break. It's almost 2 weeks, right, with me?
I know, it's been a while. Sorry about that.
No, that's fine. That's fine. I was also busy because the week that I work is pretty busy. This week, for example, I'm totally free, so I can accommodate anytime. Today, we are going to discuss your favorite topics, right? Fractals. And
Yep.
because the topics is broad,
Yeah.
and I think I will have some basic questions. So we'll focus today only on basics. And if the time allows, in the later part, I think we'll go for application and your theory specifically.
Okay.
But today, for some reason, if we cannot accommodate your theory, I think we can make a second session, right?
Okay. Yeah. It's like you say, it's a big topic. So, we'll try to get as far as we can today and then continue if we need to. Yeah.
So at the very beginning, let me ask a couple of questions. For example, I think the theory of fractal uh, is like self-similarity and complexity, right? So
Right.
it's mostly based on math,
Based on math?
mathematics, right? Equations.
Yeah. Okay. So, yes and no.
Mhm.
The idea of fractals was actually, if I can share my screen now, if that's okay,
Sure.
because I like to.
Mhm. Mhm.
No. Okay. So the idea of fractals was, of course, the term fractal was coined by Benoit Mandelbrot,
Mhm.
right? So, in March of 1980, Benoit Mandelbrot discovered discovered the Mandelbrot set. And he kind of discovered it by accident. While he was working at IBM, he was, playing around with these algorithms, these mathematical equations that they used to refer to as mathematical monsters. They
Mhm.
would call them mathematical monsters because they were very difficult to calculate, especially in the days before they had calculators or
Mhm.
computers, obviously. So yes, fractals did start out as a mathematical concept. But what Benoit Mandelbrot discovered, or what he realized, was that these crazy patterns looked a lot like patterns in nature. So fractal geometry appeared to be the geometry that nature does. So, like normal geometry, like Euclidean geometry is, a point, a line, right? A
Mhm.
surface, a volume. So, you have whole dimensions, like 1 dimension, 2 dimensions, 3 dimensions. And all of your objects sort of fit into that dimensionality. So, so the idea of fractals was what Benoit Mandelbrot realized was that you can have dimensions that are in between 1 and 2, and in between 2 and 3. So you can have fractional. That's why they're called fractals,
Mhm.
because they live in a fractional dimension. So the dimensionality is a fraction. That's why they're called fractals.
Mhm.
So
How can you have like a fractional dimension, right?
yep. That's a good question. I saw a really good demo, and I think I'm gonna try it
Sure.
here. So here's a piece of paper.
Mhm.
Okay, hopefully it won't disappear. It's gonna disappear, but here's
Mhm.
a piece of paper, and it is 2-dimensional, right?
Yes.
It's a
Mhm.
2-dimensional surface, right? Like X and Y. It's a 2-dimensional surface.
Mhm.
Okay, now I'm gonna do this. I'm gonna crumple it. Okay,
Mhm.
now it's still a 2-dimensional surface, but it occupies 3-dimensional space,
Mhm.
right? It occupies 3-dimensional space. So it's not exact, it's 2-dimensional, still 2-dimensional, it's still a surface, but
Mhm.
it occupies 3-dimensional space. So that's how you can kind of get the first, idea of how something can exist in a fractional dimension.
Okay.
So you know what I mean? So this is not a solid, so it's not really like, it's not volumetric. It's just a crumpled up piece of paper, but it is, in between, 2 and 3 dimensions.
Okay.
So that's the best way. I thought that was a really good demo of just to get the first approximation of how can you have something in between. It's either 2-dimensional or 3-dimensional, right? Well, no. And when you get these rough shapes, then, basically, that's what nature is doing. Nature is giving us rough shapes. Nature doesn't make perfect squares and perfect circles and, perfect lines. When you look at a branch of a tree, if you look at the fractal behind me, or if you look at this fractal here, it's got a branching pattern. And so, that's basically what nature is doing. So these are the patterns that nature makes for whatever reason. And, I think, one of the reasons is to increase surface area, right? So when you, so Benoit Mandelbrot, I think he either wrote an article or wrote a book, but in this book, he asked the question, how long is the coastline of Britain? And okay, so if you measure the coastline of Britain using a yardstick, using a stick that's, a yard, not a small ruler, but a big ruler. If you use a really big ruler, you're going to get a very coarse measurement of that coastline. You're going to get a number, and it's going to be, maybe it's going to be 2 miles, say. I don't know how long the coastline of Britain is, so, let's just take a 2-mile stretch of the coastline of Britain. We measure it, we get 2 miles. But then if you take a ruler that's only a centimeter, and you go and you measure, now you're measuring all the nooks and crannies of the coastline, you're going to get a bigger number. You're going to get maybe 2.2 miles or 2.2 kilometers. And, so the smaller the measuring stick, the more, the longer the coastline will measure. The coastline obviously hasn't gotten any bigger. When you shrink the measuring stick, you can measure more detail, right? And so in computer science, the measuring stick is the pixel, right? The measuring stick is the pixel. So in order to get more detail in the fractal, you have to shrink the pixel.
So in the coastline example, so it's a real object. It's not a mathematical object, right? It's a real object.
It's a real object, yeah.
So in the real object, if you use smaller and smaller stick, measuring stick, will it increase to infinity? For example, you started with 2 miles, that's a crude measurement, right?
Yeah.
But as you use the smaller stick, you already increase it to 2.3, for example.
Yeah. Yeah.
But if you go towards the down, like small scale, will it become infinity? Because that will create some like problem, obviously, because
I think it's
right?
Right. I think it's more asymptotic.
Oh, okay.
So it flattens out.
So that's the fractal geometry in basic. But how that fractal geometry relates to this Mandelbrot set, like the picture that you are showing me.
Okay, you should be able to see that now.
Yes, now I can see.
Okay, so this is a program I wrote. I can't remember if I showed this to you before, but this is a program where you can zoom, I use this little bullseye here as kind of a joystick, and you can fly through the Mandelbrot set. And so you can see there's another one there. And so that's the property of self-similarity. So the Mandelbrot set has the property of self-similarity in that I can zoom in and find more little Mandelbrots, right? So it keeps repeating, and it's never exactly the same. There should be another one right in here. Okay, so as you zoom in, you get more and more detail. I can click on this and get more detail, do it without, but you can see there's another one there. And then I can zoom in, to another point and get another Mandelbrot. So, so what's happening here is as I'm zooming in, what I'm doing virtually, what I'm doing is I am shrinking the measuring stick. I'm shrinking, so the pixel on the screen is worth a smaller amount of space, right? So I'm zooming into, you know, you can call it counter space. I'm zooming into a smaller and smaller, this would be like zooming into the atom, right? You're zooming in, you go to, there's a cell, and then you zoom in, you see, you know, you see molecules, and then you see atoms, right? So that's, you know, you're getting smaller and smaller and smaller as you zoom in. And that's how you, right? That's how you generate the Mandelbrot set. And so
how much zoom in you can do in theory? Like how many fold?
Okay, so and that's a really good question. The limit has to do with the limit to the digits of precision of my computer.
Oh, okay.
So I'm going to zoom in quickly. I'll show you. You can go quite far, orders and orders of magnitude. But I'm going to show you what happens when I reach the limit to the digits of precision. So, you know, I'm getting more and more detail, creating more and more detail as I zoom in. And this is the software I use to make fractal videos to music, right? So I can record these sequences and then play them back and then generate high resolution videos, right? So you look at, I can go in quite far. So the computer I'm using right now has 17 digits of precision, right? So that's 0.00000000000 up to 17, and that's it. Once I run out of digits, I can no longer generate these images. And so, and also as I zoom in, you see it's kind of chunky, it's kind of slowing down. So when I'm zooming in, it also takes more iterations to generate the image. So as I get closer and closer to, so here now I've hit the brick wall. I've hit my limit to the digits of precision. You can see it's all chunky, right? It's, it can't do it anymore, right? But if I had more bits, if like my computer is a 64-bit computer, but I think it's really based on the processor. So it's based on the floating point processor of the computer. So whatever that floating point processor has implemented. Now my computer, most computers, almost all of them, have a certain IEEE standard of floating point that they implement. And so you only get, you know, 17 digits of precision. But some computers can do, if you can do double that. So that would be double. And so that would give me 34 digits of precision. So I have a chunk of code that I use. If I want to zoom in more, I can use that, but then it slows things down a little bit. So I can double the number of digits of precision. Now I can go in twice as far. I can shrink down twice as much as what I can currently do right now. So that's the limit. And so the limit is, you know, the computer limits how far I can zoom in. Theoretically, I could zoom in forever, but the computer's never going to let me do that. I don't care how fancy the computer is, it's always going to have a limit. And I think nature has limits too. In fact, I think the Planck limit, you know, it's interesting. If I had twice as many bits, I could go twice as far. My limit to digits of precision would be in the order of 10 to the minus 34, right? Which is in the order of Planck length. Planck length in physics is in the order of 10 to the minus 34 meters. So coincidentally or not.
You can go beyond 10 to the power minus 34, right? If your computer processor allows?
Yeah, if the processor could do more, had more bits, then it could theoretically go. But most computers, even like supercomputers, they can only do, you know, to 10 to the minus 34 in real time, right? So like I'm doing this in real time. If I wanted to, I actually wrote a program where I could do like 1,000 digits of precision or 10,000 digits of precision, but it's super, super slow.
Okay.
Super, super slow. But I can do it. I did it, just to see if I could do it. And, it would just take like a week to just generate this little image.
So I think in YouTube I saw one of the just a video, like because they recorded the zoom in. I think they mentioned like 10 to the power 190 or something because they did it over the period of 1 year.
Yeah.
But that obviously goes beyond the Planck limit, obviously.
Yeah, and what they do is they use there would be like a special toolkit to get the extra digits of precision. And so, I would take, maybe multiple computers a year to generate one fly-through sequence. So that's, that they do that in software.
Allows you to go beyond Planck scale if you want to.
Yeah. If you want to. Yeah.
Exactly.
For sure.
Okay.
Yeah.
Okay.
Oh yeah. Yeah. It's just really hard. It's hard on the computer. Yeah.
So far my understanding is this Mandelbrot set came from a simple equation, right?
Yep.
Can you explain the equation, please?
Sure. So the equation for the Mandelbrot is z equals z squared plus c. But when I went to implement it on the computer, I couldn't just plug in z equals z squared plus c. I had to do a bunch of algebra. And then I had to extract out the real component and the imaginary. The real component, the imaginary component were two different equations. And so it didn't look like z equals z squared plus c anymore, and that really bothered me. I wanted, because if the equation is z equals z squared plus c in my computer, I want to write z equals z squared plus c, not two separate equations. Like I'd have to write these two equations here. So instead, with my two-dimensional complex number notation, I can go z. So now z is a two-dimensional number and c is a two-dimensional number, right? And now I can go z equals z squared plus c in 2 dimensions, and the notation matches the equation, right? So, that's actually, complex numbers are not that complex when you realize that numbers don't have to be like one-dimensional, like 1, 2, 3, 4, 5, 10, whatever. You can have two-dimensional numbers, and this is what two-dimensional numbers look like. So this is my notation. I came up with this all on my own, and really my goal was to implement z equals z squared plus c exactly without having to do some tricks.
Yeah, right? Complex number, I have very rudimentary knowledge, but it always tricked me because in my mind, number means you're counting and you're increasing or decreasing either by multiplication or addition or division by subtraction, right?
Yeah.
But when you have to think a number that is not, even though you increase, it doesn't automatically guarantee that the net result will increase. Because, for example, in complex number, it tends to rotate the number rather than increase the magnitude, right?
So here's what I know. Because I'm a computer scientist, I know a little bit about computer graphics and how how complex numbers work, because we use quaternions. We use complex numbers and quaternions to do rotations, just as you said. Well, here's the interesting thing. So the forward diagonal of a two-dimensional number is a scalar. So it scales things. That makes sense. The backward diagonal is the imaginary component, and it rotates. So this backward diagonal, without knowing anything about complex numbers, I already knew that the backward diagonal of a matrix, it creates a rotation. So now, and I also knew that imaginary numbers create the rotation. So all of a sudden, imaginary numbers make sense because the backward diagonal of a matrix, when you're doing matrix multiplication, creates rotation. So, and there's no concept of imaginary anymore in my notation. There's no like there's no mystery like square root of -1. You can't take the square root of -1. Like that's all sort of a misunderstanding of imaginary numbers. All of these values are real values. There's no imaginary, like these are all just numbers, A0, B0, like these are all numbers, real imponderable numbers, positive and negative numbers. There's no imaginary concept in this whatsoever. It's just forward diagonal and backward diagonal. I would call these forward numbers and backward numbers if we had to label them differently. But, you know, so this actually simplifies, you know, makes the notation looks ugly. It's not as pretty as, you know, z equals z squared plus c, but it's way more logical and there's no confusion. That's why I call my paper Demystifying Complex Numbers, because I take all the mystery out of the imaginary, you know, component. Because when you take an imaginary number, so these are the identities. These are, this is the positive real identity. So instead of 1, the positive real identity is 2 ones on the forward diagonal. And the negative identity is 2 negatives. And then the imaginary identity is there's plus minus and there's minus plus. And these are called complex conjugate. These are complex conjugate. But, you know, so these are the 4 identities in my notation. And that, you know, so those would be literally the identities of the 2-dimensional numbers.
In simplified way, can you explain how that equation z equals z squared plus a complex number, how that equation generates the infinite number of different magnitude and different position, all like every time you look at it is different, right? It generates a new pattern. So how
does it make a fractal? How does it make a fractal? Is that really the question you're asking? Okay, so that is a really good question. Okay, so in order to make a fractal, have you ever heard of iterated function systems?
Little bit. You can explain to me, you know.
Yeah. Let me know if you can see this.
Yeah, I can see your screen.
Okay, so iterative function systems. Let me just take some images. Okay, so iterated function systems are used to generate things that look like, you know, things in nature, like a fern, right? So there are a lot of fractals that use, so what they do is they take a simple pattern and they, you know, do 3 transformations on it. You do 3 transformations. So to make all these fractals, you need to do at least 2, but usually 3 transformations. So you take a simple pattern and you scale it, you rotate it, and you translate it. And that's it. You can take any pattern, you know, all of these things are done the same way. You take a simple pattern and you, especially for the fern ones and the ones that look like trees, you take a simple pattern, you scale it, you rotate it, and you translate it. Those are the only 3 transformations, you know, that you can do. There's no other ones, right? There's scaling, rotating, and translating. And you get a fractal, right? Almost every time.
By scaling, you're saying increasing or decreasing the size, right?
Increasing or decreasing the size.
Now, the rotating is self-explanatory, but what do you mean by the last part?
Translate, to shift. So if you look at, say, this fern here, let's have a close-up look at this fern here. So you've got this big pattern, right? But if you look here, you've got the same pattern, but it's scaled, it's rotated, and it's translated, right? So then you get another one, so you translate and rotate and scale, right? So this pattern here is the same as the one next to it. The next one is a little bit scaled, maybe a little bit rotated, and it's shifted down the line.
Okay.
Right, it's shifted. So those three transformations are used to make iterative function system to make these fractal patterns. And, you know, they use it to create, same kind of thing to create, you know, landscapes that look perfectly real, or cloud formations that look perfectly real, just by using this iterative process. So it's an iterative process. You take a pattern, you scale it, rotate it, and shift it. Scale it, rotate it, and shift it. So then you see there's a little one here that's exactly the same as this one, that's exactly the same as this one, only it's scaled and it's rotated this way and it's translated to a different location.
So that means you're feeding back the answer of the previous step to the next step.
Yeah.
To begin with.
Yeah.
So that's how you put the multiple. Okay. So for z equals z squared plus c, in step one, there will be some answer, and that will become your new z, and you square it.
Okay, so
something like that.
Yeah, something like that. So now z equals z squared plus c, because the z and c are complex numbers, all the transformations are actually built into this equation. So all those three transformations are built into this formula. And it took me a long time to figure that out. It's like, why does this make a fractal? Oh, so the squaring scales, right?
And you're also eliminating the minus sign because you are squaring.
Yeah, so the squaring can, you know, if you have a number smaller than 0, then squaring is going to make it smaller. If you have a number bigger than 0, the squaring is going to make it bigger, right? The translation is the plus c, so the translation is obvious, plus c. So yeah, if you don't put plus c, there is no fractal, right? You need the translation. It's a very important part of the formula. And the rotation, the spinning, is also in the square, because when you square a imaginary number, when you square the imaginary component of a complex number, it creates a rotation. So the squaring, when you multiply two imaginary numbers, that creates, or if you two complex numbers with an imaginary component, you get a rotation. If there's an imaginary component, you get a rotation. So all of the transformations that I talked about, the scaling, the translation, and the rotation, are built into this formula. And that's why it creates a fractal.
You just mentioned without the C part, there will be no fractal. Why is that?
Because the translation is a very important part of creating a fractal. You need all three transformations.
Okay.
Right? You need all three. Otherwise, everything just ends up in the same spot. You need.
Yeah, it will just increase the number, like a Fibonacci series. It's like positive direction or negative direction. It will go in one direction rather than making pattern, right? Without the sequence.
Yeah.
So Fibonacci sequence, for example, you add the previous two and find an answer, and that becomes your next number, something like that. So when 1 equals 2, then 1 and 2 equals 3. So the series continues and it goes forever, right?
Yep.
But here, it's also similar, because in step 1, whatever answer you get, in the next step, you put that thing as Z and you square it again.
Correct.
You find the answer, again you square and plus you add a complex number.
Yep.
Now, why they are so different? For example, Fibonacci sequence just increase and generates new number every step. But why this reiteration creates so many patterns? So what's the fundamental difference?
Okay, so I think I'm going to try and, okay, I'm going to shut this one down. I'm going to show you another program. I think it's easier to explain with a demo. So let's see. So can you see a fractal on the left? It's got white and
black and white
patterns. Okay. So I can actually show you what the trajectories are doing. I can actually show you what it's doing. So all the points in this white region here are the points that escape after one iteration. So what you can see, can you see this line on the left here?
Yes, the blue line, yes.
Yeah, so this is the starting point. So so what I'm doing now is I'm displaying the real and imaginary components up here.
Mm-hmm.
So this point was the real component was 0.75, blah, blah, blah. And the imaginary part is minus 1.2, just an arbitrary number, which I am using the left one to control and the right one to display, right? So wherever I move my mouse on the left, that's where it's going. So the first iteration, it escapes. So what happens is this is the radius 2.0. So here's the middle of the circle. The middle of the circle is right here. And the radius, if I measured the radius, this would be a 2.0 radius. Okay, so what I'm looking for, so you know how if you take 2 times 2 times 2 times, 2 squared and then square that and square that, it's gonna explode to infinity, right? It's gonna expand to infinity. But if you take a number smaller than 0, it's gonna get smaller and smaller and smaller and smaller. So if you only had real numbers, if this wasn't a complex plane, then if you took, 1.2 or something and multiplied it, eventually it's going to get to 2. And once it escapes to 2, then 2 squared times 2 times squared, whatever, will go to infinity, right? So, but if you take a number smaller than 1, 0.09, and square it, you get, a number smaller than 0.09.
It always remains less than 1, right? If
Yeah.
you square a number less than 1.
It gets smaller and smaller and smaller. Okay, so if this was just a real plane and a real plane, you would get, just it escapes. You'll have a boundary, a radius 1.0 boundary where everything outside of that's going to escape and everything inside of it's not going to escape. It's going to get smaller and smaller and smaller. But with the complex plane, you get complex behavior. So everything on the outside, of this black region, which is literally the Mandelbrot set. So the black region is named after Benoit Mandelbrot. These are the points that never escape. I call it a black hole. It is analogously a black hole, and we can get into that later. But basically, the points on the inside don't escape, and the points outside this boundary, the complex boundary, always escapes. It just takes longer. So let's have a look. So everything in this area escapes after 1 iteration. And then the next layer, it takes 2 iterations. So now you can see this was the first point, this was the second point, and then it escaped. And then if I go to the next layer, now it's 3 iterations. So it escapes, 1 iteration, 2 iteration, it escapes. So as you can see, the closer I get to this crazy boundary here, the more crazy this pattern is. See, now this is 6 iterations, and it's taking a very strange path, right? It's not taking a normal path. It's going all over the place, and then it escapes, and then I know. Once it's out here, then I can stop iterating. I don't need to iterate anymore because I'm done. It's gonna go to infinity. So that's what my program tests for the condition. If it escape, if I find a point outside this boundary, it escapes, and I call that the escape velocity.
I think here I have one question. So I think you mentioned if the starting number is already more than 2, it will blow up.
Yeah. So here I'm out.
Yeah. Okay.
It already escaped. Like I don't even have to iterate that. I have -1 iterations. Actually, it should be 0 iterations.
And if it is less than 1, it stays inside a region because it converges towards smaller number.
If it was a real number, yeah.
Yeah. Okay. Now can you so between 1 and 2 are the unknown region of numbers, where can you predict that this will remain inside the Mandelbrot set, or you have to do the?
No. So the Yeah, so the less than 1 is really just with real numbers. Now that, because now that we have a complex plane, we have complex behavior. We have, I think that's why they call it the complex plane, because it exhibits complex behavior. So it doesn't behave like, so there is a boundary. So instead of the boundary being a nice radius of 1.0, it is a complex radius. There is no one radius, right? It is an infinite number of radii, right? This boundary. So it's not one radius. So it's the opposite of what just normal real numbers do, right? Normal real numbers would be bigger than 1 gets bigger and smaller than 1 gets smaller, and that would just be a really simple picture. It'd just be a circle. So this complex numbers create strange behaviors because of those 3 transformations I believe I was telling you about. Because it's doing it's scaling, translating, and rotating. And you can see the rotations. Now I'm going to show you the points on the inside because you can really see the rotations going on. Okay, so the points on the inside, I'm going to zoom in a bit here so you can see it better. I'll make it a little bigger. So, so you can see the points on the inside are spiraling in to this point here. So they're going here, 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 here. They're and this is another reason I call this a black hole, because these are actually falling towards singularity. Okay, they're falling towards a point that's infinitely small. Right? So if I zoomed in on this, I have a video, I don't have it handy, but I've got a video where I actually zoom in on this point here. And you see the same pattern as you go down, all the way down, until I hit that, the limit to the digits of precision, then I can't calculate it anymore. But so the points on the inside behave significantly different than the points, oh, okay, sorry. Come on, there we go. Why is that not working anymore? Okay, so in what you're seeing on the right is I'm just not connecting the points. So when I connect the points, you can see the path it's taking. But when I don't connect the points, you see, oh, it kind of looks like a galaxy, right? Yeah. Doesn't that kind of look like a galaxy? But then when I connect the points, it looks like a spirograph, basically. So this is what the complex numbers inside the Mandelbrot set are doing. They're like spiraling in towards singularity. And the closer you get to this boundary out here, right? The closer you get to, so both on the outside and the inside. So on the outside, the closer I get to the black region, the more complex, you see how complex that pattern is becoming? Yeah. Right? It's super, like it's filling it in. It's got so many, but on the inside, it's the same thing. The closer I get to the boundary, the bigger and the more complex that pattern becomes. And of course you can see it spinning, right? You can see as I'm changing, yeah, I can see. It's spinning. So the spin is built into the z equals z squared plus c, right? Which is kind of neat. Right. So this is, not too, again, this is, I'm not going to say it's my discovery, but I seem to be the only one that's interested in this phenomenon, right? So what I did was I wrote a program where I was looking for, like, right at the edge. You can see as I go very close to the edge, it kind of explodes, right? It kind of explodes. So on the inside, it does this. I go close to the edge and then it explodes and then it, So I really wanted to see what was going on at this boundary condition, because that's what in chaos theory and fractal geometry seem to always occur at boundary conditions. Every, when I do research into fractals in quantum mechanics and fractals in semiconductors and fractals in all kinds of things. There always seems to be some sort of boundary condition where it's a transition. Whenever there's a phase transition, you get fractal geometry. Whenever you get, either a boundary condition or a phase transition, this would be like a phase transition, you get fractal geometry. So this is, part of my research has been to find all the ways that nature does this. And, they find fractals now in quantum mechanics and they don't know why, but they seem to always have some sort of boundary condition. So, this is a boundary, this is a complex boundary. In my theory, I call it an event horizon, or you could just call it a horizon, which is fine. It's a horizon because a horizon separates, the upper from the lower or whatever. So what I discovered was, now I'm going to show you this from my paper. Hopefully you can see that. So can you see fractal cosmology?
I can see.
Okay. So as I got closer to that, so I wrote a program to randomly choose points in the complex plane, iterate them, and the ones that took the most iterations, I saved those. So some of them took 100,000 iterations or maybe up to 1 million iterations. Like I was looking for really super high iteration counts, more than 10,000. Like I wanted really, really high ones. And so the more iterations, the closer I am to that boundary condition. So the more iterations I have, the closer I am to that boundary condition. And actually I wrote the program not knowing what I was going to find. And I found something really super interesting. Okay, what I discovered was, so these images on the bottom of this figure here are patterns that I got from the Mandelbrot set.
Okay.
Right, so each of these was generated just with one complex point. I took a single point, just like I was doing in the demo I just showed you. The demo I just showed you, those trajectories were just one point. You take starting point, you iterate it, and maybe up to 1 million times, or 1,000 times, or 10,000 times. So each of these, so I just wrote a program and let it run, let it generate a whole bunch of them, and I only saved the ones that were, high iteration. And the next day I went back and I looked, and I was really shocked because what I found was these patterns looked very much like cosmological objects. So the objects on the top are real cosmological objects. This is the Cartwheel Galaxy and the Stingray Nebula. This was the most shocking one actually, because this algorithm is generating these shapes that are very, very, very hard to explain in like this shape here, which happens quite a bit, this sort of cross shape, it looks like a stingray, that's why it's called Stingray Nebula, are generated just with this simple z equals z squared plus c.
Yeah, this is amazing, because when you showed me the picture, I thought all of them came from your iteration.
Yeah.
The top row is actually
those
the
are
Okay.
Those are real cosmological objects. So
that's amazing.
Yeah, so that's pretty neat. It's pretty neat, and that's why this is what got me to writing my paper, the Mandelbrot set as a quasi-black hole, because all these cosmological objects are also associated with black holes, right? Planetary nebula have black holes. Galaxies have black holes. This one here on the right was actually the most surprising. This is called Einstein's cross. Now,
the right one, right?
Einstein's cross is supposedly gravitational lensing because they can't explain it any other way. So they explain it, it must be a bunch of quasar, or one quasar in the background and one in the foreground, and it's gravitational lensing and making this pattern. Or it just formed that way. because I found one that, you know, when I saw this one down here, you know, it's not, it's, you know, more contrived, but the pattern, it's the pattern that, you know, that it has almost exactly this pattern of intensities. And so, you know, it really got me thinking now, like, is this really gravitational lensing, or was it just born that way? Right? Was it just born that way? So they can't really say. They can speculate that it's gravitational lensing, but they can't say 100% for sure it's gravitational lensing. They don't know how this object is formed. I think this object was just born that way, and that we'll find other ones. I think they have found other ones that look like that. So gravitational lensing exists. There is gravitational lensing. It's got a very particular signature, and I don't think this is gravitational lensing. But if it is, then fine. But we'll never know. Like, we can never know exactly. But the fact that I found a pattern that looked an awful lot like this in my, you know, my fractal generator, you know, makes me, you know, think maybe we should rethink this a little.
So inside most of the galaxies, I think the current cosmological interpretation is there is a black hole, right? Inside most of the big galaxies. Now, the black hole is the black part. If you, I'm just trying to understand the analogy here. If the black hole part of the galaxy is the equivalent of the black part of the Mandelbrot set, then the galaxy is the formation of variety of different kinds of geometric shape of galaxies is similar to your boundary zone of the black. You just showed me the black versus the start of chaos, right? Because beyond the black zone, if you go away from the horizon, things becomes apparently random without any clear pattern, right?
In a real galaxy or in the fractal?
No, in the Mandelbrot.
Oh, okay. So I mean, with those trajectories.
Yeah, trajectory becomes uncontrolled.
So that's more, the Mandelbrot set is more of a parameter space, I think, than I don't think it's really meant to be to represent physical reality, even though it does kind of look like physical reality, right? So here's an image I did. The one on the right is from the Mandelbrot set. The one on the left is a spiral galaxy, a real spiral galaxy. And I couldn't help but notice that the spiral arms are exactly the same, right? They follow exactly the same path. So of course, a galaxy is a little more messed up than, you know, the Mandelbrot set's a little more contrived, a little more too perfect, maybe, even though it is chaotic. It's, you know, if I took this and ran a gravity equation on it, it would end up looking like this. So, you know, this is sort of perfection and this is imperfection. But this spiral pattern, which is really important because, you know, it's got a phi scaling, right? 1.618 phi, you know, the golden mean, the golden ratio, Fibonacci spiral, it, you know, appears in the Mandelbrot set, obviously, because there it is, and it appears in nature. Right, and this one has sort of this thing off here, and this has like a thing over here. Like geometrically, these are freakishly similar to me. Right, so the Mandelbrot set basically just generates patterns that nature makes.
Yeah, I can see. It's like...
And so the black hole here, you know, you've got a black hole in here, and actually this, so here's an interesting thing, and I made a mistake at one point thinking that there would be a Mandelbrot in this region here. So I went looking for it, couldn't find it. Well, Mandelbrots, the you know, self-similar little mini Mandelbrots only occur at bifurcation points.
Bifurcation?
Yeah, in the Mandelbrot set. So that's a little hard to explain, but you know, there's not Mandelbrots everywhere. Let's just say there's certain places where many Mandelbrots will form
Okay.
in the Mandelbrot set, and there's places where it won't. And there's no mini Mandelbrot right here, right? You're going to find them more at bifurcation points, like in here, where it seems to bifurcate, where the space seems to bifurcate. So that's another clue. That's another clue as to, you know, how nature works, because, and that got me thinking about magnetism, right? Getting back to magnetism, because magnets have a bifurcation, like right in the middle. The block wall of the magnet is the bifurcation point, and nature seems to like to bifurcate things. So it branches, right? So I don't think that answers your question, though.
My question was like, it's like basic principle, because in Mandelbrot set you are putting your initial variable is only two, one number
Yeah.
and one
Yeah.
complex number, and your operation is also very simple. You are squaring it and adding it.
Yeah.
So, but maybe in nature, by using very similar reiteration principle, but the number of variable may be a little bit bigger, higher.
Yeah.
So
Yeah.
that's why it's not identical, but they're very similar in principle.
Yeah.
Okay.
Yeah. Yeah. So, you know, when to make the Mandelbrot set, you have to iterate, and if it escapes, you paint it a color depending on how many iterations, and if it doesn't escape, you paint it black. So that's just the standard rendering. Now, for my program, it's a little different. When I'm plotting, let me go back to this program here. So when I'm plotting these trajectories, that's just one point. So I take one point and I iterate it, and I actually generate the this pattern here. So this is just, you know, basically what I do is you know, this is my test. So I look and see, is it converging rather than diverging? And then if it's converging, I paint it black. And if it diverges, then I paint it a color depending on how many iterations, right? So if we go back to the original one, okay. So if it's one iteration, in this one, I paint it white. And if it's two iterations, I paint it black. If it's three iterations, I paint it white. And if it's four iterations, you know, this is just a simple, you know, diagram. So I can show you, you can, with this, you know, I could do colors. Obviously, I could do colors. But, and what you would do with the colors is you would say, okay, one is red and two is green and three is blue and four, you know, whatever. So, and it's a little more complicated than that, because I want to do in between. So I have a thing called the escape velocity, which is this one here, where I can actually calculate in between the iterations, right? So instead of, you know, I get a you know, number that's not a whole number. So you can see it's changing, it's a continuum. So as I get closer, that number gets bigger, and I can use that escape velocity to do a really nice, see the picture in the back here where you can see it's got a nice smooth gradient. It's not like jumpy like this. And that's the numbers I use, this escape velocity. I use that to paint, do a nice gradient in between, so it looks more pretty, I guess you could say.
Okay.
So, you know, each point either generates a trajectory, you know, depending on how long it takes for that trajectory to escape, that's how I determine what color to paint the fractal at that point, right? So each point.
That's how you generated the first picture that you showed me. When you zoomed in, every layer was different color coded. Okay.
Yes, exactly. So that gave the nice smooth rendering. It looks pretty. It looks, you know, and then, you know, I can choose whatever colors I want for, you know, for that, for the video, for the animation.
Yeah. Now I have just a general question. So based on my rudimentary knowledge in basic mathematics, so when we did in my school or college, the mathematics that involved the complex number, So your goal was to find a answer that is still not complex because you wanted to convert the complex number to a real number so that your answer becomes a real number. Because, for
Yes.
example, I'm talking about just elementary school, high school level mathematics. Because our teacher used to say that the complex plane is useful only for calculation. It's not real because you cannot buy any stuff with a complex number of money, for example. You have to have a real value so that it becomes useful. But here I can see most of the data point remains inside the complex plane, right?
Yeah.
Yeah, so
Yeah.
in that regard, so what will be the practical utility other than doing calculation and modeling complex structure? That's fine. But is there any real utility by data set inside the Mandelbrot set? Like real
Like,
world utility. For example, by using the pattern, can you predict some real material or real complex scenario like leaves or trees pattern? I'm just posing
yeah.
question because I don't know the
Yeah.
answer.
Yeah. So predictions are a big part of science, obviously. People
Mhm.
want, if you have a theory, it's no good unless you can make a prediction, right? That's it. That's what I've been told. Now, I don't buy that. I don't buy that. I don't think, basically, if you have a model in it and it mimics things that nature does, then that's good enough. Like, you know, maybe I could predict, like, yeah, I know what you're thinking, maybe the stock market or something like that. Actually, I have a friend who's an economist. His name is Blair
Mhm.
McDonald, and he does fractal. He uses fractals in um, his economics. He does fractal economics,
Yeah, the
and he's
stock market
also,
chart looks to me fractal because the jump
yeah.
and
There
down,
are, okay, so
ever like everlasting new pattern every time in the stock market.
yeah,
Price action.
exactly. And I actually thought of a possible application, and maybe I'm giving away a really good trade secret here, but for like Bitcoin,
Mhm.
for like something like Bitcoin, where you have um, keys, I think they're called, where you have key pair. I can't remember the terminology, but there's some possibility of creating
Crypto hash,
keychains.
some
Sorry,
hash,
what?
some crypto hash number or something,
Yeah.
some cryptography or something, right?
Yeah, exactly. And so actually I found a paper, somebody sent me a paper where they used the Mandelbrot set, but I thought of a way to use it that would be really,
Mhm.
like really easy to generate a super long code that no one would ever be able to crack,
Mhm.
right? And using this kind of thing.
Mhm.
But I
Mhm.
could do like 10,000 digits of precision or something like that, and
Okay.
generate really super long keys. So that's one possible real life application for this kind of complexity,
So one
maybe.
will be one you just mentioned the stock market price pattern, and another one with
Yeah,
cryptography and security, like a cyber security or something.
yeah,
Okay, now just another one question. I'm asking all kinds of questions
it's
because
fine.
asking question is easy.
Yes,
Okay,
answering questions is fun
uh,
for me.
if you already know it is easy, yeah. So another so when the matter becomes matter, so before the matter becomes matter, there must be some interaction, calculation, all kinds of things going on, like at quantum world, for example. But some of the calculation actually falls onto itself without generating a matter that might be a black hole region, right? And some of the part that successfully generates the matter and it can fall out that goes into the beyond the horizon, and
Yeah.
that can be a galaxy or matter. That can be another one, like uh, use in principle, not necessarily practical. How the Mandelbrot set can be used to model the galaxy formation, etc.
Okay. So yeah, relating this to real life is
Mhm.
a little complex. complex, obviously. I think the Mandelbrot set, to me, it's more like a teaching tool, right? It's not necessarily to be taken too literally. And so I think, I don't know if it was last time or the time before, where I talked about something called the principle of incommensurability.
Yeah,
right?
I think I saw
Right?
it.
Where you have basically what I said was, you've got the principle of incommensurability says that, well, I'm making it up, but it says that there are two domains. The universe works in a dual principle, or a dual domain, which I call space and counter space, or, you know, darkness and light, or, you know, so you can think of all kinds, you know, there's all kinds of ways you could express this principle. And so what the Mandelbrot set taught me was, you know, the universe exists because of the principle of incommensurability, because of the two domains. Okay, so, you know, mainstream physics does not have a concept of counter space, but I would call this counter space, and I would call this space. But space is nothing and counter space is nothing. What is something is this event horizon, right? All of the fractals, all of the pretty fractals that I generated with that program as I'm zooming in, are at this super complex boundary, right? So my, you know, my intuition is telling me that the universe has two domains, counter space and space, and matter is between space and counter space.
Okay.
So galaxies and particles and any complexity that we see in nature, life, this is life, can only exist at the event horizon of a black hole. And so we're, you know, you're not going to find life where there's no black holes, right? So, you know, so my idea is that a galaxy is the event horizon of a black hole, and you are the event horizon of a black hole, and atoms are event horizons of a black hole at that scale, right? So black holes appear at different scales, and so in my model, the atom is actually a black hole, and this would be the nucleus, and these would be the electron shells, right?
Okay.
They're shells. They're just like electron shells, right? And analogously, of course, right? So there's a lot of really neat sort of analogies you can make when you start looking at this, not as a physical, this is not physical space necessarily, but it can tell me how physical space can come about. And so through the, you know, as the universe iterates, so the universe is continuously evolving, is continuously iterating. So time and iteration are the same thing, right? Time is, you know, emergent property of change, and iteration is the agent of change. So as the universe iterates, it becomes more and more complex. And so, you know, those things I can say I'm 100% sure that's true, at least, you know. So I can't really say that this is what the universe is going to look like, even though I can find things in the Mandelbrot set that do look like galaxies, almost exactly like the one I showed you before. And so it's almost like this is like a hologram. Almost like, and that's where you want to get into the hologram. I don't want to get into the hologram yet, but it's very similar to that principle, because this is a surface, right? It's a boundary. It's a boundary, and that's in everywhere there's boundary conditions, you often find fractals, or you find complexity, you find complex patterns at the boundary condition between two domains.
Yeah. So in this picture, I think I'm just putting another one idea. So because this picture is generated from the equation that has a complex part to begin with, and we ourselves consider we are in the real plane, but suppose the situation is just flipped. Somebody or something that we don't know, because by definition we don't know the unknown. but something or somebody or some mechanism, if they initiate the algorithm like this from the complex brain, then from their perspective, we are the complex brain.
Right.
So if we can generate a everlasting complex like event horizon, all kinds of new things, and if they or something else who lives in the complex brain initiate the algorithm, so from their point of view, it will remain in their complex brain, which is this reality, for example. So even by exercising this mental math, it gives you a clue that how it can be generated even in theory, so that
Yeah.
the mirror is like dream world versus real world. So our dream world is unreal to us, but suppose the dream world is real, like the movie Inception, we are the dream of the dream world, for example.
Yeah.
It's like flipping the scenario.
Yeah.
Yeah, it's really interesting. So definitely we'll talk about the relationship between fractal and hologram. And I think you have some theory that you can combine these two and you can propose something new in the next session.
It's not even really my theory. It's actually a mainstream theory that combines, black holes, fractals, and the holographic principle.
Perfect. Yeah. I'll be
definitely. It's a lot.
But definitely, I'm learning a lot, and I'm just amazed by your like broad, like thinking capability.
Good enough for one show.
Yeah, I think good enough for today. Yeah.
Okay, great. So
next session we'll definitely talk about your next topic, hologram and fractal and other relations.
Yeah.